We have already presented 2 videos on the TCCS. In TCCS Part 1, What is TCCS?, we focused on the basic construction and function of the TCCS. The TCCS includes electronic fuel injection, electronic spark advance, idle speed control, the Toyota variable induction system, diagnostic functions, fail-safe functions, and backup functions. In TCCS Part 2, System Inspection, we studied the functioning of system circuits and methods of inspection. Recently, as in the case of the Lexus LS400, the TCCS has been linked with other formerly independent systems through various ECUs. However, the basic operation of the TCCS itself remains the same. In this, Part 3 of the series, we will take what we learned about the TCCS's basic functions and individual systems in Parts 1 and 2 and apply it to actual examples in malfunctioning vehicles. Let's look at our first problem. The check engine warning light goes on and does not turn off. When asked, the customer explains that the light first went on while the car was moving, and since that time goes on and then remains lit whenever the engine is running. However, the engine appears to be running normally when the car is moving. Upon inspection, the following problems were pinpointed. The engine is sometimes a little slow to start. Except for this, everything is normal. After the engine starts, the check engine warning light remains on. However, the engine appears to be running normally. In the normal mode, the diagnostic code is 13. Let's try to think of some of the possible causes for this problem. Diagnostic code 13 indicates trouble with the NE signal circuitry, or with the G1 or G2 signal circuitry. To pinpoint the cause of the malfunction more closely, run a check in the test mode. Set the test mode by connecting terminals TE2 and E1 of the TDCL and switching the ignition on. When the engine is started, the check engine warning light goes on. Connect terminal TE1 and read the diagnostic code in the test mode. In this case, diagnostic codes 13 and 17 appear. Diagnostic code 17 indicates a malfunction of the G1 signal circuitry. To confirm this diagnosis, use an oscilloscope to check whether the G1 and G2 signals are being properly input to the ECU. The G2 signal is normal, but there is no G1 signal input. This means that there is a malfunction at some point inside the area illustrated by the diagram. First, check the G1 sensor resistance. Since it is between 950 and 1250 ohms, the G1 sensor is okay. Next, we check the harness, starting with the continuity between ECU terminal G1 and the number 1 cam position sensor terminal 1. There is no continuity. The problem appears to lie here. Let's check each harness. First, check the harness between ED1 connector terminal 2 and number 1 cam position sensor terminal 1. No problem. How about the continuity between ECU terminal G1 and ED1 connector terminal 2? No problem here either. So where's the cause of the malfunction? There are still some places left to check. That's right, the ED1 connector. First, is the terminal securely inserted into the connector? They seem to be okay. Next, let's check if it is a good connection. Aha! Terminal 2 is loose. This seems to be the cause of the problem. Change the terminal and clear the diagnostic code before testing again for confirmation. This time the engine starts smoothly and the check engine warning light goes off. So this was the cause of the malfunction. Why is it that if one of the two G signals is missing, it takes a little longer to start the engine? In the case of the LS400, when the G signals are normal, they are output one after the other, switching once for each rotation of the crankshaft. In other words, in a properly functioning engine, in the time it takes for one full crankshaft rotation, one of the two G signals is input to the ECU, then the injection timing and ignition timing are set, and the engine starts. However, when one of the G signals malfunctions, there is only one signal pulse for every 2 crankshaft rotations. Therefore, for the ECU to set the injection and ignition timing, the crankshaft may have to turn a maximum of 2 times. That is why the engine is sometimes a little slow to start when this problem is present. The next problem we will look at is high idling speed. Here is some information concerning our test case. 1. The idling speed seems much higher than normal. 2. When the coolant temperature is low, idling speed becomes even higher. 3. In the normal mode, the diagnostic code indicates normal. 4. The ignition timing is too advanced. 5. The accelerator pedal link and dash pot are functioning normally. Please take a moment and think for yourself about how to continue troubleshooting from here. Let's stop the video for a few minutes. Well, what ideas did you come up with? Let's continue the troubleshooting procedure together. First, some of the possible causes of high idling speed include Air conditioner switches on. Idling speed control system malfunction. Throttle position sensor malfunction. Neutral start switch malfunction. Water temperature sensor malfunction. Intake air temperature sensor malfunction. To pinpoint the cause of the problem, first run a check in the test mode. The check shows diagnostic code 51. This indicates possible trouble with the neutral start switch signal, the air conditioner switch signal, or the throttle position sensor IDL signal. First, let's check the neutral start switch signal using the circuit tester. Move the shift lever from neutral to drive. No problem. This circuit is okay. Next, test the air conditioner switch signal. Switch on the air conditioner. It's fine too. This circuit is also okay. Finally, check the throttle position sensor IDL signal. Depress the accelerator. There's no change whatsoever. That means there may be a malfunction in this circuit. First, check the voltage at IDL1 and E2 on the harness side connector of the throttle position sensor. No problem here. In other words, up to the harness everything is working normally. So let's go on to check the throttle position sensor. This may be difficult, so check it using a service wire. There is no continuity. There seems to be a problem with this circuit. As per the repair manual, first adjust the IDL contact. After the adjustment, check the IDL contact again. Now it's okay. And the idling speed is also back to normal. The diagnostic code indicates normal, so the cause of the problem was poor adjustment of the IDL contact. But why does poor adjustment of the IDL contact cause the idling speed to increase and the ignition timing to be too advanced? When the IDL contact is off, the ECU thinks the throttle valve is open, so it stops ISC valve feedback control. This is why ignition timing is advanced and engine idling speeds up. Our next case involves a vehicle that won't start. Although it was fine yesterday, Today it suddenly refuses to start. There are several symptoms. 1. Cranking continues for over 2 seconds, but there is no combustion. 2. In the normal mode, the diagnostic code indicates normal. 3. In the test mode, the diagnostic codes are 17 and 18. 4. The spark test is normal. Now please think for a moment how to continue troubleshooting from here. Let's turn off the video for a few minutes. Did you come up with any ideas? Let's take a look together. Since in the test mode the diagnostic codes are 17 and 18, some of you may have thought G1 and G2 were the trouble spots. However, if both G1 and G2 or NE were malfunctioning, diagnostic code 12 would also be indicated. To check whether this happens in practice, let's try the same thing with an engine which starts normally. First, with G1 and G2 open, set the engine to the test mode. Then, after more than 2 seconds of cranking, check the diagnostic codes. They are 12, 17, and 18. The same occurs when NE is open. So, when both G1 and G2 or NE are malfunctioning, diagnostic code 12 will always be indicated. In this case, since diagnostic code 12 is not indicated in either the normal or test mode, we can conclude that there's no malfunction in both the G1 and G2 circuits or in the NE circuit. So what could be the cause? Let's think again. In the normal mode, the diagnostic code is normal and the spark test is fine, but the engine won't start. What should be checked next? That's right. We're going to have to check the fuel system. First, let's take a look at fuel pressure. Check to see whether the fuel pump is operating by seeing whether the pulsation damper screw lifts when check connector terminals plus B and FP are connected with the ignition switch on. The screw is not moving, and you cannot hear the fuel flowing through the delivery pipe. Let's see whether there is voltage at the fuel pump motor connector. No, there is not. There must be a problem with the fuel pump circuitry. Let's continue our inspection. First, with the ignition switch on, check whether or not there is voltage at check connector terminal plus B. There is voltage, so there is no problem up to this terminal plus B. Next, with check connector terminals plus B and FP connected, let's measure the voltage at ECU terminal FPR. Since there is voltage, this circuit is okay. Now let's see whether the fuel pump works when the ECU FPR terminal is grounded. The relay works. the fuel pump motor starts to run and the pulsation damper screw lifts. So we know that when the circuit is grounded, point A closes, current flows through the resistor to the fuel pump, and the fuel pump begins operating. Based on these observations, the problem will probably be found in the area indicated here. Let's start with a continuity check of the fuel pump relay. There is no continuity between terminals 1 and 4. To be sure, check the rest of the circuit. Instead of using the fuel pump relay, connect terminals 1 and 4 directly using a service wire and check whether the fuel pump motor runs when you do this. We can hear the fuel flowing through the delivery pipe, so there is no problem here. It is now clear that there is poor contact at point B. This is the source of the fuel pump relay malfunction. We replace the fuel pump relay and check whether the engine starts normally. It's fine now. As you have seen up till now, when there is a malfunction in this part of the fuel pump circuit and the fuel pressure in the fuel line falls, the engine won't start. When this problem occurs while driving at high speed, insufficient fuel reaches the engine and the vehicle begins to slow down. The next case we will look at was diagnosed as a rough idling problem. Examining the results of the diagnoses, we came up with the following. The diagnostic code showed normal in both the normal and test modes. The matrix chart suggests several possible trouble areas. It would take an awfully long time to check all of them. There must be some simpler, quicker way. Please take a few minutes to think for yourself how to proceed with troubleshooting. Keep in mind that there is no vacuum leakage and that the fuel quality and EGR system are fine. Let's turn off the video for a little while. Well, what did you come up with? We all know how to check rough idling by doing a power balance check. However, when the engine has as many cylinders as the LS400 and the high-tension cords are covered by a layer of resin, this method is not very convenient. In such cases, it's far more effective to troubleshoot using an oscilloscope to check the oxygen sensor signals. First, we check the main oxygen sensor signals. The left and right bank signals are different. There seems to be a problem with the left bank. Since we have narrowed the problem down to the left bank, we can now use the power balance check method to continue inspection. First, the number 1 cylinder. Since the idling becomes rougher, we know the number 1 cylinder is trouble-free. Next, the number 3 cylinder. It's okay too. The number 5 cylinder. Okay. Number 7 cylinder. There is no change. The idling doesn't get worse. This means that there is no combustion in the number 7 cylinder. So, the next step is to check the resistance of the number 7 cylinder high tension cord. There seems to be an open somewhere in the high tension cord. Let's install a new high tension cord. The rough idling stops. So, the source of the problem was the damaged high-tension cord. This is an example of effective use of the oxygen sensor signals. However, remember that if an over-lean or over-rich condition lasts for too long, the ECU also stops the oxygen sensor feedback control for the bank that is normal. So in some cases, the oxygen sensor signal waveform cannot be used for diagnosis. In such cases, the engine must be revved several times, or the EFI fuse must be removed to clear the memory. One of these actions should restore the oxygen sensor signal to normal. Here is another case of rough idling. This vehicle is in worse condition than in the previous example. Diagnostic checking and physical inspection yield the following results. 1. In the normal mode, diagnostic code 25 is indicated. 2. When the diagnostic code is cleared and the car driven again, the diagnostic code indicates normal. 3. But when we check it again after switching the engine off, then starting it again and driving the vehicle, diagnostic code 25 appears once more. Four. Rough idling continues as before. Please take a few minutes to think for yourselves how to continue troubleshooting in this case. Let's turn off the video for a few minutes. These symptoms are rather strange, don't you think? Let's have a look at diagnostic code 25. Diagnostic code 25 signifies an air-fuel ratio lean malfunction. As in the previous case, let's check the oxygen sensor signal waveform. There is a malfunction in the right bank. So next we run a power balance check on the right bank at the distributor side. No change in cylinder number 2. There is a change in cylinder number 4, so it's okay. Cylinder number 6 is okay too. There is no change in cylinder number 8. This means that there is no combustion in cylinders number 2 and 8. Upon inspection, The high-tension cords seem to be okay. Perhaps there's a problem with the injection circuit. First, measure the voltage at terminal number 20, which is connected to cylinders number 2 and 8. The voltage is normal. Next, inspect the ECU by checking the signal waveform. There's no signal. Let's compare it with the other terminals. Only terminal number 20 is malfunctioning. So we have found that the terminal number 20 circuit in the ECU is not working properly. This means we have to replace the ECU. We check again after replacement. The rough idling has disappeared. So the ECU malfunction was the cause of the problem. Now let's think back on the situation at the time when we were checking the symptoms of this problem. At first, Diagnostic Code 25 was displayed. We cleared the memory and ran the engine. This time, in the normal mode, the diagnostic code indicated normal. However, when we checked a second time, Diagnostic Code 25 appeared once more. Cases like this, in which the diagnostic code appears only after the second occurrence of a problem, are due to what is called two-trip detection logic. What happens is that information on the malfunction is temporarily stored in memory and is manifested only after the problem occurs a second time. However, when we set the test mode before running the engine, the problem can be detected with only one test. Please try to use the test mode effectively. These diagnostic codes are also output by the same two-trip detection logic. Let's look at just one more case. Here too, the symptom is not starting, but the cause is very difficult to pin down. Our symptom check revealed the following. 1. The check engine warning light does not go on when the ignition is switched on. 2. Although the engine cranks, there is no combustion. 3. No diagnostic code whatsoever is indicated in both normal and test modes. 4. When the ECU W terminal is grounded, the check engine warning light goes on, so the problem is not a burned-out bulb. Please take a few minutes to think for yourselves about how to continue troubleshooting in this case. Please turn off the video for a little while. Since no diagnostic code has been indicated, the diagnostic code system does not help at all. So, to continue troubleshooting, we will have to turn to the repair manual. Let's start with number 1 in the matrix chart, the ECU power source circuitry. First, we measure the voltage between the +B, +B1, and E1 terminals. There is voltage, so the ECU power source circuit and the ground circuit are okay. Next, run a spark test to check the ignition signal circuit. Neither the right nor left ignition coil sparks. Let's check whether the ECU is outputting an IGT signal. Measure the voltage at the IGT1 and IGT2 terminals. Both of them show 0 voltage. This is a problem. Next, go on to step 6. Disconnect the igniter and check the voltage again. As before, there is no voltage. There does not seem to be a short circuit inside the igniter. Next, check to see whether the harness is short-circuited to ground somewhere between the ECU and the igniter. There is no problem here. This means the ECU may not be working properly. But before replacing the ECU, let's consider possible reasons for the lack of an IGT signal. Here are some possible causes: ECU malfunction, ECU power source malfunction, ECU grounding malfunction, NE signal malfunction, G signal malfunction, VC signal malfunction. So, as you see, the ECU itself is not the only possible cause of the problem. We have already tested the ECU power source and grounding. Both were normal. Let's check the remaining possibilities, the NE, G, and VC signals. First, let's check the NE and G signals when the engine is cranked. They are fine. Next, let's measure the voltage at the VC terminal. 0 voltage. There is a problem with the VC signal. What are the possible sources of the VC signal malfunction? Let's check the throttle position sensor circuit and the airflow meter circuit, both of which are related to the VC signal. Disconnect both parts and measure the VC voltage. First, the throttle position sensor. Even disconnected, there is no voltage. The throttle position sensor does not seem to be related to the malfunction. Next, disconnect the airflow meter. 5 volts. When reconnected, the voltage returns to 0. There is something strange here. Let's try starting the engine with the airflow meter disconnected. It starts. As you know, the engine will start even when the airflow meter is disconnected. This is one of its fail-safe functions. However, when we reconnect the airflow meter, the engine dies. This means there may be a malfunction in the airflow meter. Let's check the resistance between the VC and E1 terminals of the airflow meter. There is no resistance. There seems to be a short circuit in the airflow meter's VC circuit. Let's try replacing the airflow meter. The engine starts. So the cause of the malfunction was a short circuit inside the airflow meter, not a problem with the ECU itself. This case shows that to pinpoint the source of a malfunction, it is essential to understand the construction and operation of all systems in the TCCS. It also shows the great importance of thoroughly investigating a problem before replacing often expensive parts. We hope you have found this video useful. But before we finish, let's review the essential points to keep in mind when troubleshooting. First, listen carefully to the customer's description of the problem. Don't jump to conclusions. Next, try to reproduce the situation the customer describes or simulate it and check it out for yourself. And remember, when troubleshooting, it is essential to know all the systems thoroughly, particularly the ECU terminal signal voltages and signal waveforms. For effective troubleshooting, know and use the ECU fail-safe functions such as those for the water temperature sensor, intake air temperature sensor, airflow meter, etc. Recently, an increasing number of cars employ two-trip detection logic, so run simulation tests at least twice. Master all these points and you will soon be troubleshooting quickly and accurately.